So we'll start just in a few minutes. All right then, let's begin. Oh, forgot my camera. Sorry, 1 second, guys. Can you guys see me? Awesome. All right, so welcome to Chem B41 Experiment 3. Right, and we're going to get it. Sorry, someone saying something? There is weirdness on my camera. Do you guys see my camera? Okay, weird. I'm gonna turn off my chat. Is it better? Okay, I can't obviously tell because I turned off my chat. Okay, so I'm gonna turn on my chat and let me know if it gets worse or better. Okay, so it seems like my chat is causing some problems, so we're going to have to absolutely stop. So I've turned off my chat, which means that I cannot communicate with you guys during this lecture. But that's okay. I'm sure it'll be okay because for the most part, I think there aren't too many problems. Yeah, sorry about this, guys. And if you do need anything, feel free to use contact me on my email. Actually, now that I see that, you guys probably can't see my email in the way that it's phrased. Hold on, let me turn off. There we go. Move all the stuff. Hold on. And let's make it black so you can actually read it. You know what? Just delete that. Sorry, I didn't design this. It's fine. Yeah, I didn't design this slide. I just took it from the TAing thing. So here is my email. So if you have any questions, please feel free to contact me on the email. Right? And let's begin. Is it? I think it's lagging. Sorry, 1 second. Okay, now my computer's frozen. Sorry, give me a second. I'm gonna close it and reopen it. So what I'm going to do is I'm going to go over and I'm just going to read out the names on the attendance sheet, and then I will check you guys at the very end on who's here and who's not. And that's how we're going to do it today. Hope that's okay. So Jotham Abraham, Muhammad Ali, Sanya Anil, Huang Bui, Zayama Inam, Zhao Fang, Yang Lin Liang, Anjali Mahadio, Argavan Majidi, Jia Mi, Jordan Morin, Zino Patel, Alia Pathan, Jatin Sarviswaran, Asmi Shukla, Barsansha Singh. So please guys don't actually text me anything or in the group chat because it's only going to mess my computer up. But Practical One, happy to have you here. Right? And lovely Tuesday morning, and I hope this is okay with you guys. Please email me if you have any questions. Honestly, I will respond. Maybe not right now because I'm going to be doing the presentation, but right after the presentation I'll be able to respond, and hopefully we can get this to work out. right? So once again, 1,000 apologies for this. Anyways, without further ado, I guess let's begin. Alright, so for experiment 3, it's pretty straightforward. We're going to be talking about melting point, then polarimetry, and then molecular modeling. And we're going to have some few questions for you guys. And really, because this is a very highly... What we're going to do instead is that... Alright, part 1, melting point. Oh, sorry. Part 1, melting point. Melting point. Melting point is the temperature at which the liquid and solid phases are in equilibrium at 1 atmospheric pressure, right? And temperature at which the vapor pressure of solid and liquid phases are equal. So basically, it's the, as the name kind of suggests, it is the point at which a chemical starts to transition between phases, right? Solid to liquid and these sorts of things. And what we want to do is we want to measure it. It gives us a measure of the purity of the compound, right? And for pure compounds, there's a very sharp change from solid to liquid state. I think we covered some of this before as well, but that's totally okay. So, very sharp change. For impurities, if impurities are present, the melting point is decreased, right? So the more impurities there are, the lower the melting point, and the intersection of solids and liquid and solid curves occur at a lower melting point. So what that means is, so if this is solid, vapor, and liquid, so the intersection between these occurs at a lower melting point, and so the object melts sooner, right? And one thing to mention is that melting point, although we always say melting point, is not actually a point. Sorry, I think I forgot to describe this a little bit, so I'm going to describe it. So the figure. So in the figure, what you see here is that there's a solid curve intersecting with 2 liquid curves, right? So the liquid curves are PA1 and PA2. PA1 is the pure solution with no impurities, right? So this is no impurities. PA2 is the solution with impurities, right? So it intersects. So as you can see, like the solid curve here, you see how it goes down? The intersection of T2 is much lower than that of T1, right? And that's kind of what a melting point curve kind of would look like, right? And yeah, basically the reason why the melting point changes is because as you add impurities, you disrupt the intermolecular forces between the molecules, and that allows it allows for decreased strength. So think of it like a very well-defined shape. Like imagine like some interlocking compounds, right? So they fit very nicely into each other. They're crystalline structures, right? So they're very pure. So they're crystals, right? So they fit perfectly, right? There's a regular lattice, all of it very optimally bond to each other. Now, what happens is that as you introduce an impurity, so let's say we introduce this pen as an impurity. So now, notice that my fingers before used to be perfectly aligned, now it just can't. There's something sticking out, right? And imagine in 3 dimensions, you wouldn't be able to get the same structure, right? So what happens is that any presence of impurities prevents the optimal formation of the crystalline structure, which then decreases the overall required to break the bonds, because it's no longer optimal, it's suboptimal. I hope that's clear. If you guys do need a little bit more of a definition or more description, I'm happy to talk about this more over email. Maybe we can set up a Zoom time. That's clear. Now, next up is the eutectic point, right? And the importance of the eutectic point is that no melting occurs below the eutectic point. So here, take a look at this graph here. So, and we'll talk about the graph and we'll talk about it together. Actually, don't be concerned. There's a lot going on, but we'll definitely handle it together. So on the far left here, we have 100% of compound A. On the far right, we have 100% of compound B. In between compound A, like 100% of both, is a composition, a mixture of both of them, right? So, for example, at here, you have 50% A and 50% B. Right? And now on the y-axis we have the temperature. So at what temperature, things will happen. So let's take a look at point R. Right? So at TR, the temperature at R, above this temperature, the mixture will be liquid. Below this temperature, it'll be solid. Right? And so to read the composition, you just have to take a look at the x-axis and the y-axis, right? And you can go through it. So it becomes much easier, I think, in that sense. Now, there's a special point, the eutectic point, at which no melting occurs below the eutectic point, right? It goes straight from solid to solid. Like here you can see it's decreasing, right? It stops decreasing and starts increasing again. So basically, when you take a look at this, you'll notice that M is the lowest possible melting. So what that means, basically, take a look from left as you go from left to right. You know, you're going from A to B, right? You'll notice that the temperature is decreasing until M, and then it starts increasing again. M represents the lowest point. There's no point at which it'll be like it's the lowest point of melting. There's no point less than that, basically, right? And anything below M is always going to be solid, always, right? And so basically that is the eutectic point. All right, so moving on from that, I hope that's clear. Again, if it's not clear, email me and we will have a discussion on this. Don't worry, it's very simple. It's not that important, to be honest. It's literally just that it's the lowest point at which the lowest temperature at which the mixture will melt. There's no point. There's no mixture, no binary mixture, I guess in this case, that will melt at a lower temperature. That's it, right? It's the point that's the lowest. I don't know how else to explain it. I know a lot of students usually get confused, so I'm going to say it one more time, just because I can't communicate so well with you guys right now. Right? The eutectic point is the point on the binary composition graph that melts at the lowest possible temperature. Right? So just basically just draw a graph. Whatever is the lowest point, that's the eutectic point, or eutectic temperature if you want to go to the temperature. Right, hopefully that's clear. If not, we can talk about it over email or Zoom or something. All right, so melting point procedure. I think you guys saw it in a video last time, but that's totally okay. So basically, you obtain a recrystallized acid compound. You measure the melting point, and you use it to measure and compare the value. So if you have, compound A, B, and C, A has a melting point that's like 22 to 24 degrees. B has one that's like 50 to 60 degrees, or that's too much, 50 to 51 degrees. And C you have that is like 113 to 114. And then you run your compound, your unknown compound, and you get, let's say, 52 to 53. You automatically know it's compound B. Right? It's very easy to identify compounds this way, although it's not perfect because there are lots of compounds overall. Like if you have no idea what the compound is, you'll still have no idea, right? I mean, you'll be able to exclude certain things, but if I just say that there's a compound with a melting point of 15 to 16 degrees melting point range, what is it? There's no way for you to know what it is, right? And so that's good. Alright, so melting point and procedure. So you grind up the crystals, so whatever crystals you got last time, you take them, you put them into a component. You don't really have to grind them, generally they're just okay. Then you take out these capillary tubes, right? One end is open, one end is closed. What you do then is that you take the open end and you kind of jab it into your crystals, and then until you get some inside, then you drop it in this dropper stick. So you literally put it in, it's like a long hollow tube. You take your capillary, right, and you just put it on top, closed end at the bottom, and drop, and it goes tuck, 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 right, and then it stops. And as that happens, the stuff that you kind of put in at the top will eventually start to move to the bottom, and it'll look like this, right? And then you can see it in the machine. It looks like this, and you can measure the melting point. There are some videos for you guys to watch, and I downloaded them, so hopefully I downloaded the right ones. Oh, well, sorry, this is polarimetry. So once again, no, I did not download the right one. Okay. What happens when you click it? I don't know why I'm so bad at this. I thought I did it. Oh, this isn't the video part. Okay, that explains. Okay, there's no video here. I'm sorry. This is just a description. Yeah, so there's no video here. That explains why. It is a technique. There's no actual video there. Right? Anyway, so melting point table and sheet. So this is the data sheet I think you guys are given. And here are some melting point ranges. Here are some compounds and the corresponding melting points. Right? So again, if you get a compound with a melting point of, 47 to 48, you know it's benzophenone. Right? Whereas if it's 122, you know it's benzoic acid. Right? So if you have a list of possible compounds and you have the melting point of your compound, it's easy to determine which one it is. And so you can go from there. Alright, part 2, polarimetry. Alright, so polarimetry is a very, very cool technique. It allows for one to calculate the concentration of an unknown sample, if you know the compound, obviously, using the specific rotation. Okay, now let's go over this a little bit. So in this is the equation for specific rotation. So we have specific rotation over here, and it is dependent on a particular temperature and wavelength of light. If you change the temperature or wavelength of light, you'll change the specific rotation. All right? Now, what you have after this is that, oh, by the way, before we continue, temperature is in degrees Celsius, not Kelvin, so that's unique in this, I guess, a little bit. Now, typically, I guess it could be in Kelvin, but you have to be very careful of units. Wavelength is in nanometers, very important, and typically 589 nanometers. And the reason for that is because it's the D line of sodium, and that's a very good wavelength to use. It's a good question why, but yeah, it's really good. So here we go. So what you want to do basically is you want to take a look at this equation here. So when you do your rotation, what you do is that you take a compound. There's a video that explains what's going to happen. This is going to sound a little bit confusing. Then you'll watch the video. Then you'll probably watch this again in the recording. Then you'll understand what I'm saying, probably. Right? It's much easier in the physical lab. So what you do is you fill up. Come on, there we go. You fill up a tube basically with your sample, right? And once you fill up the tube, I think that there's a better picture over here. So it looks a little bit like this, right? And you fill up the tube with your sample, and it's clear. So it's like a telescope almost, right? So you can look through it, and there are these little bulges on the top and the bottom. Those bulges are to trap air, so that bubbles don't come in the middle. The bubbles go towards the top, and you get like clear solution through. Right? And there's a real picture here. So see, you can see the huge bubble there, but that's okay. It doesn't cause any problems because you see through it. Right? And what happens is that as you see through it and you use plain polarized light. So we're going to go back. So now that you've seen what it looks like this. Right? So this is the polarimeter 2. What we're doing is that we're taking a light source. We're using a lens to polarize the light. Right? So now we have complete, like light, generally light is polarized, is non-polarized in every direction, right, going all over the place. So we use a polarizer and an auxiliary prism to get light in one plane, right? So ordinarily light's just everywhere. It's random, it's chaotic, it's everywhere, right? We don't want that. We want it to be in one orientation. Then as it goes through our tube, the compound rotates the plane polarized light. So it used to be straight, now it's tilted. Right? And then it goes to the analyzer, and then we can see the tilt. And based on the degree of tilting, we can then put it into our equation here, and we can get it to see. So what this means, this rotation, is the optical rotation that you observe. Right? And of course, there's a manual and an automatic. Right? And that's it. Yeah, there's a manual and automatic, and you just get the rotation. Now, here are some very other important things as part of this equation. C stands for concentration in grams per 100 mils. A lot of students lose a lot of marks. It's not molarity, it's not molality, it's not any of that fun stuff that you guys just learned and learned the importance of. It is grams per 100 mil. Right? And L. L stands for the path length. And this is also in a strange unit. It's in decimeters. So it's in how many every 10 centimeters, right? So 1 decimeter equals 10 centimeters. So again, you gotta watch out for these units because they're going to kill you guys. And there are very tricky questions you'll be faced with that, given the path length of this many centimeters, what is the specific rotation? And then you'll punch in the centimeters and you'll get some ridiculously high number or low number, I guess, because 50 centimeters is like 5 decimeters, right? So dividing by 50 versus dividing by 5, completely different numbers. I mean, not that different, it's only off by 10, but, right? It's a very different answer anyways. You'll lose tons of marks on it. So you've got to watch out for those units, right? So, and the specific rotation is specific for every compound, for enantiomers particularly. Right? So if you have R and S enantiomers, they will rotate light in opposite directions but of equal value. Right? So what happens is if, let's say, the R rotates in this direction by 15 degrees, the S will rotate in the other direction by 15 degrees. Right? Clockwise is by convention positive, right? And counterclockwise is negative. So I hope that's clear. So again, this is a very important question. They love to ask this question in quizzes. They love to ask this question on exams. It's very easy, but it really tricks a whole bunch of students up because of the units, right? So we'll go over it one more time. This is the specific rotation equation. It depends on the temperature and the wavelength, right? 589 is the nanometers is the wavelength, usually 25 degrees Celsius, room temperature, right? 22, 25, something like this. Right? Now, then you have the observed rotation over the concentration times the path length. In our case, we have a path length of 1 decimeter. That is 10 centimeters, but with the unit you're going to put is in decimeters, so it's 1 decimeter. Right? And then you can rearrange this equation and you can solve for a different thing. So let's say you have sucrose in here, right? So if you have sucrose and you want to find the concentration and you know that its rotation is, let's say, 15 degrees and the specific rotation is 5, so you just do the equation. So you multiply both sides by C, right? C cancels on this side, and then you put the specific rotation down. So you get 15 over 5 times 1, which is 3, right? And again, you got to watch out for units. Sometimes specific rotation, if you look up the literature value, it'll be in non-decimeters and gram per 100 mil units. You have to use the right units. I don't know if I'm stressing it enough or if that's coming out clearly, so I'm just going to say it one more time, super stressed for you guys. You have to watch the units. A lot of students, really good students, I've seen them lose marks. Right? This is the first time we're having like this online kind of thing. Well, I guess last year a little bit too, but like for the past 4 years or something I've been doing this course, and so many great students, they lose marks because they don't look at the units. Alright, I think I've stressed that enough. Time to move forward. Right, so here's how it works. Plane polarized light, depending on the enantiomer, right, it'll clockwise or counterclockwise, and different enantiomers, different directions. Mixture of enantiomers, no change because they cancel each other. Alright, manual polarimetry. So we talked a little bit about this before. So we mentioned there were 2 types of polarimetry. Right? The first is manual. Yes, so sorry. Brain freeze there. So the first is manual, the second is automatic. Right? And as you can probably guess, the manual polarimetry is less accurate than the automatic polarimeter. Right? And we'll talk a little bit about why that is. So what you're going to do in this lab, and you guys obviously are just going to watch, or not watch, even talk about, I guess, the sucrose solutions. So what you're going to do is you're going to get 2 sucrose solutions. You're going to put them into the tube. Right? So you're going to open up one end of the tube. So there's a glass cover disc, and there are some like components, I guess you can call it. Like this metal thing is just hollow, it's just like a cap. There's also a cap just to hold the lens down, and then the lens connects to the glassware, right, that you put the sucrose into. So what happens is you fill this up, you put out all the pieces, you close it up, and then you try and trap the bubble on the top here. And again, I'll show it to you here. There it is, trapped. Right, and you make sure that everything is connected, you make sure everything is not leaking, and you make sure to wipe the outside. You don't want anything weird on the outside. Alright, then you rinse the tube with H2O. Oh, well, actually, first you'd rinse it, then you'd put your sucrose solution in. That's just obvious. You should always, if you get something, rinse it before you put your chemicals in, because you don't know who used it before you. And let's say that you have a very dilute solution. So let's say that you have a solution of like 0.1 grams per 100 mils, right? But the guy who used it before you, that guy had like 400 grams per 100 mils. It's impossible. It'll like super saturate and it'll like precipitate out. But sorry, and right, so it's not possible. But you can imagine even a tiny drop of that 400 grams per mil. Okay, I'm gonna use a real number, 4 grams per mil, right? Which is still 40 times more than what your sample had. It's going to throw off your results because even one drop of that in your solution is going to greatly increase the concentration. Right? So you always want to wash it with water before you put your solution in. Then you fill it completely as best as possible. You try and cover it. Ensure any bubbles are trapped in the, I guess it's called the bore region. I call it the bubble trapping region, because that's exactly its purpose. Alright, then what you do is that when you put it through and you look through it, you'll see this, I call it a moon, right? So it's like a circle, right? And it looks like this, right? If you put water in it, it looks like this. But as you put different compounds in it, you'll find that it's not like a full circle, like you cut off a portion of it, right? So in this case, if it's counterclockwise, then it's going to be only lit on one side. I mean, it's going to be lit on the right side, and vice versa for clockwise rotations, right? And what you do is that you read it with the vernier scale. Very difficult to pronounce word, not such a difficult concept though, right? So here's how you read it, right? So what you do is that when you get it and it's like half, right, what you want to do is you want to turn the knob. There's a knob. You can't see the machine, unfortunately, but there's a knob. You turn the knob until you see the full moon. I call it the full moon, but until you see the full circle. Right? Now, before you do this, of course, you will have done the same thing with water, and make sure the machine is calibrated. To calibrate the machine, you put water in there, you'll see the full moon water, no enantiomer, no plain polarization, so it'll just be straight perfect. Right? You'll line up the 0 with the 0. Okay? So that's what you do. You line up the 0, 0, then you throw out the water, then you put your sample in there, and then you put it in, and then you see like the half moon, then you turn the knob until you see the full moon again. Right? When you do that, you'll notice that this scale drops. Right? See, it's supposed to be at 0, 0, and then it moved down 1. Right? So that's 1 degree. Now, that's not just necessarily 1.0000, it's 1, and then now we have to find the decimal. To find the decimal, and I think the next slide has it better, right? You take a look on the left-hand side. So the number that it goes down, so here we saw it went down by 1, right? So you look, oh, by the way, it's equivalent on both sides. Sometimes they show the vernier scale like on the left-hand side and on the right-hand side. In the machine, you'll see it on both sides. It doesn't matter which direction it's on. What matters is the direction change from 0, 0, right? Like from the perfect alignment, the change. Now, what you do now is that you take a look, and we're going to use this one as an example, and we're going to go to the real picture, right? So you go here, so it changed from 0, 0, it went down by 1, 2, okay, and then it's not exactly 3, but it's close to it. Right? So it's down, it's 2 point something, right? It's not 3, it's less than 3, but more than 2. 2 point something. So now what you do is that you look at all of the lines on the vernier scale, and you look for the first line that lines up perfectly. Right? So you look at 0, nope, doesn't line. You look at 1, it's hiding behind the circle oval, but it doesn't align. You look at 2, doesn't align. You look at 3, just a little tad bit off. Then you look at 4 and you go, aha, it aligns perfectly. Right? And so 2.4 would be your rotation, like your angle, right? So again, we're going to go over this again and the picture, and then we're going to take a look at the real life image here. So again, you take a look for the whole number, you take a look at how far below 0 is from the 0 line. Right? So you take it and then you go 1, 2, okay, but not 3. So it's between 2 and 3, so it's 2 point something. Then you look to see which of the vernier scale aligns perfectly. And you go 4. Aha, it's 2.4. Now, a couple of things you can automatically tell. Oh, sorry, let's talk about the real system here. Right? So again, if you look here, you can go and say, okay, 1, right? So it's 1 point something. And then what's the first one that aligns perfectly? I think 0 might align perfectly, but maybe it's a little bit off. 1 I think does. I also think 2 does, but so in my case I would say 1. So we know it went down by 1, and then we know that the decimal, the first one that lines, is also 1. Right? So what does that give us? We get a value of 1.1. So now obviously very clearly you guys can tell there's some strong weaknesses of this method. Number 1, it's highly subjective. I mean, I said 1.1, but some of you guys are going to be looking at that and go, Saeed, are you crazy, man? It's clearly, 1.0. Right? And like your neighbor, if you were doing this with 2 people, like you'd have another guy who's like, what? That's crazy. It's obviously 1.2. And you guys would argue from dawn until dusk. Is it 1.1 or 1.2? And the third guy will come in and he'll say, oh, it's 1.4. Right? Well, because it's off by a little bit, and because every direction you look at, like everyone's height is a little bit different, so like you'll look at it from a slightly different angle, and then what's straight to you might not be straight to me. Some people are just naturally better. For example, my wife is an architect, so she can just tell straight lines. I don't know how, like she can tell if it's off by even a little bit, but I can't. Right? So depending on your own subjective level of line straight detectability, right, you're going to get different answers. And it can range. Usually it won't range so much, but there have been cases, and like real experiments, like students are doing it and in the lab, and I've had a case where one person was saying it's like 2.2, another person was saying it's 2.6 and 2.8, and there's no way. Each of them look at it and they have their own points of view, and there's no way to distinguish between whose is right. Not only, so that's one thing. So the vernier scale itself is highly subjective and difficult to tell, right? But beyond that, even if you look at this methodology, how do you know when it's exactly perfect? The full moon, I mean, right? Like, I mean, theoretically, yeah, sure, you turn it, you get the full moon, but there must be like a 0.01 degree or 0.1 degree left or right that, maybe I see it as a full moon, but you don't see it as a full moon because maybe your eyes are better. Maybe not. Maybe you see orange better or something. Right? And it's so subjective. So to summarize, the manual polarimetry scale is more subjective than the automatic one. Right? So the manual scale, you actually have the subjectivity in actually getting that full moon circle, and then you also have the subjectivity in looking through and reading the vernier scale. Right? So I think I've stressed that enough. And then you go from there. And that's about it for this, I guess, right? And then you get it. Now we have how to operate a automatic polarimeter. And let's use our video.
Polarimetry machines are used in chemistry in a wide variety of ways. Their main purpose is to measure the angle of rotation of an optically active substance using polarized light. This polarized light will either rotate clockwise or counterclockwise, and the amount it rotates will indicate the angle of rotation. Polarimetry is
I just want to say, I'm sorry to stop you guys. I miss wearing lab goggles. Oh my goodness, I haven't been in the lab for so long. It's crazy. Sorry, okay, back to his speech. And this was a student of mine, by the way. No, bright guy.
Light will either rotate clockwise or counterclockwise, and the amount it rotates will indicate the angle of rotation. Polarimetry is important in chemistry as it allows one to distinguish between enantiomers using optical activity as a measuring point. There are key tests in chemistry that are used for the identification of substances, such as the melting point tests. However, these tests are proven non-conclusive for the identification of enantiomers, as they have identical melting points and physical properties.
Sorry, just to reiterate that a little bit. So enantiomers cannot be detected with melting point. So we just talked about melting point for like the last 20 minutes, and now I'm telling you that it doesn't actually tell you enantiomers. It'll tell you the difference between compounds, but not enantiomers. Sorry, let's let Daniel continue.
Within the automatic polarimeter machine, there is a light source and a fixed polarizer. The polarizer will convert monochromatic, non-linear light into a unidirectional light. As this unidirectional light passes...
You know, now I'm thinking, why did I bother trying so hard to explain this? This video is going to be so much better than me.
...through a glass tube. The polarizer... Within the automatic polarimeter machine, there is a light source and a fixed polarizer. The polarizer will convert monochromatic, non-linear light into a unidirectional light. As this unidirectional light passes through a glass tube containing an optically active substance, the plane of polarized light will begin to rotate. Finally, the rotated polarized light exiting the glass tube will be detected by the analyzer that measures its angle of rotation and produces a reading for the sample. The formula below illustrates the different variables a specific rotation depends on. The specific rotation is a literature value measured in degrees of any given chiral molecule. It can be found in scientific papers or online. The specific rotation is affected if the wavelength of light used to illuminate the sample changes or the temperature of the solution is altered. The main variables that can affect an observable rotation are concentration of the substance and the length of the glass tube containing the optically active substance. Prepare a solution with your unknown substance. Weigh out the desired mass substance. Record the concentration of your unknown substance in your lab notebook.
Note, he has his book with him as he measures. That's how you're supposed to do it.
Using a funnel, transfer it to a volumetric flask. Rinse the weighing tray and funnel with a glass pipette using deionized water. By using deionized water, fill the volumetric flask to its midpoint. Fill the volumetric flask up to the line with the glass pipette.
Notice the meniscus.
Stopper the flask. Dissolve the solid by shaking the volumetric flask up and down. In order to find the optical rotation of your substance, you must first calibrate the automatic polarimeter.
Very important.
To do this, fill the sample holder using a syringe with deionized water. Draw out deionized water and insert into the proximal end of the polarimeter sample holder. As you begin injecting the fluid, be sure to maintain an angled orientation of the sample holder. That will help to ensure no air bubbles will be present. A waste beaker should be placed under the distal end to catch any spillage coming out. You may stop injecting water once the liquid can be seen coming out of the distal end. Cap the distal end of the sample holder, and then cap the proximal end after removing the syringe. Wipe down the vessel with Kim wipes, making sure the outside is dry. Remember to check for bubbles that may be present, as it can impact your reading. Use a white piece of paper behind the sample holder and look through the clear lens.
Do you see how you can see the full circle at the end? That's what you're looking for.
If you see a small white spot inside the lens, that means the holder is free of bubbles. If you don't see a white spot, then you must
So this is a bubble. This darkness, that's a bubble. So when we talk about bubble, we weren't talking about that tiny thing before. We're talking about this guy.
Fill the sample holder correctly. Next, open the hatch in the machine and insert your blank. Note that the sample holder is placed between the two rails inside the machine towards the right side. Make sure the tube touches the right wall. Close the hatch and press 0 to calibrate the machine. After the calibration has completed, open the hatch and remove the blank. Empty the sample holder completely using a syringe filled with air and a waste beaker under to catch any spillage. You will repeat the previous procedure to find the observed rotation of your unknown substance. Pour sufficient amounts of sample from your volumetric flask and into a beaker. Using the same syringe, draw out your solution from the beaker and insert into the proximal end of the polarimeter sample holder. Don't forget to tilt your sample holder and use a waste beaker to catch any spillage. Cap both ends of the sample holder and wipe down the vessel with Kim wipes. Remember to check for bubbles that may be present, as it can impact your reading. Open the hatch and insert your sample holder. Press start once the sample holder is correctly placed and the hatch is closed. Read the observed rotation from the display screen and write it down in your notebook. Open the hatch and remove your sample. Uncap and pour the solution into the waste beaker. Rinse the sample holder with deionized water and empty all contents into the waste beaker. Repeat the washes several times to ensure complete clearance. Ensure all apparatus components are properly sterilized and returned to their designated location. If you are given an unknown concentration, you can calculate and solve using the formula given. Remember that the concentration units are in grams per 100 milliliters. You should also compare the observed rotation with various literature values. The chiral compound with the specific rotation best matching your experiment result is your unknown substance.
Awesome, that was a fantastic video. And that was on how to use the automatic polarimeter. This is all literally what he just said, so I'm just gonna go there. I turned off my speaker there. Right, so he literally just said all this. So you guys all saw it. I'm just gonna go past it. Alright, some questions. I'm just gonna help you guys answer them. You guys can think about them too in your spare time. So, and again, if you have any questions on these questions, feel free to email me. I'll put up my email at the very end of this this talk as well, right? So that way. What do you guys want to call this, by the way? I guess it's a online lab. I mean, I feel like lab is not the right word for this, but anyways, we're at the end of this lab. So, why must plain polarized light be used and not normal light? Well, as we saw in the video, that we want to see the change in rotation, right? And that normal light has every angle of light. So even if it all rotates, since it's all symmetrical and in every angle, you'll never know what the amount of rotation is. That's why you need to use plain polarized light. Why is it necessary to indicate, or question 2, why is it necessary to indicate the wavelength and temperature that the experiment is performed in? Sorry, too early, guys. It's too early. Anyway, so the reason why it's necessary to indicate the wavelength and temperature is because the specific rotation depends on it. So the rotation, the amount that each compound will rotate per gram per 100 mil, right, is actually dependent on the wavelength being used to measure, because they're each absorbed and interact with the salt, with the sugar or compound differently, and the temperature, because temperature will actually change concentration as well. Alright, number 3, you've been using deionized water. Why do you need to? Right, because non-deionized water would contain some impurities, iodine, salt, whatever, that could interfere with your results. Why would air bubbles pose a problem? Oh, sorry, that's question 4. Why would air bubbles pose a problem? Well, as we saw when you looked through the video, right? You saw that when you looked through it, like with the air bubble, it became so dark, so you couldn't see any light. The air bubble prevented light from traveling, and then would, thus affect your results. How would a mixture of stereoisomers impact the optical rotation obtained from the polarimeter? Right, so a mixture of stereoisomers would cause it would cause it to cancel, because let's say you have both of them present, they'd both just cancel because they rotate in opposite directions, so nothing would change, right? And intermediate between the two. And if let's say you have slightly more, so let's say you have like a 2-to-1 ratio or something, then the rotation will be skewed slightly towards the greater yield, right? So let's say you have 3 R's and 1 S or something like that, right? So it won't be exactly 75% of the specific rotation, I think, but it'd be pretty close, something along those lines. Alright, so what is optical purity and what is enantiomeric excess? Optical purity is the ratio of the observed specific rotation to the specific rotation of the pure enantiomer. So what that means is that let's say you have sugar and the specific rotation is 2.4, let's say, right? And you look at it and you get 2.3. So there's something a little bit wrong there. It's not as pure, right? But if you get 2.4, it's totally pure. What is enantiomeric excess? Right, so enantiomeric excess refers to the excess of one enantiomer over the other in a mixture, right? And it's measured by molars, by moles. So the ratio I was talking about, like the 3-to-1 or whatever, right? So whichever one is more. So that's what enantiomeric excess is. Pretty straightforward. If you have any questions, please email me and we can talk about them in length. Part 3, molecular modeling. Alright, so this is something you guys I think are going to be doing at home. You have like a question sheet or something to answer, and it's very straightforward. So this is the chart basically that we're going to use for this. So here at the very top you have isomers, right? So, and you want to go through and see how they're all subdivided, right? And you can see, constitutional, then stereoisomers and so on. And you can find all different types here. And at the very bottom we find our friends, the enantiomers. Alright, so isomers. So there are 2 types of isomers, constitutional isomers and stereoisomers. So constitutional isomers are compounds that have the same molecular formula but different connectivities, right? Like, so for example, we all know that cyclohexane, for example, has like carbons and hydrogens, right? But we know that the alkane, hexane, is different. But they have, I think there might be a difference of like 1 hydrogen or something. But okay, let's say it's a double bond. right? But they have the same formula, but they're different physical structures, right? So that's a constitutional isomer. A stereoisomer is a compound that has the same molecular formula and same connectivity, but a different spatial arrangement of the atoms. So we're going to talk about that a little bit more, right? So what do we mean? Did it change? Oh yeah, okay, we did. So yeah, you can have two types of stereoisomers. You can have configurational and conformational. So conformational, basically, it's just rotation about a single bond. So let's say you have like a methane group or dichloromethane, let's say, for example, right? So you have the chlorines on the sides, right? And you hold one chlorine bond as your angle, so you're looking at it, chlorine, carbon, then you have the rest of the tetrahedron, right? So you have one chlorine and two hydrogens. Well, you could rotate that, and you'd have the chlorine on this side now, and the two hydrogens here. Same molecule, just a small rotation among about a single bond. Then you have configurational compounds. So they cannot be interconverted by rotation about a single bond, right? So that would be like double bonds or triple bonds, and it's not the same. You can't just go and say, oh, there's a double bond, there's a single bond, just rotate it, and you get the same molecule. It is not the same molecule. There are two types of configurational isomers, right? The first is geometric, and then you have the cis and trans EZ because it's about a double bond, and then you look at which part or split of the double bond is the larger portion, right? And then you have the EZ or cis trans, right? And then you also have optically active isomers, so those are our enantiomers and diastereomers. Right? So enantiomers are non-superimposable mirror images, right? And diastereomers are... Okay, so this is going to get a little bit confusing. So diastereomers are non-superimposable and non-mirror images. I wonder if I can change that. Maybe not, okay. But they're non-superimposable and they're non-mirror images, right? So they're neither. And we'll see an example of that coming up. Right, so here we go. Maximum possible number of stereoisomers. Now we're done going through the flow chart there, and again, you guys can take a look at it and familiarize yourselves with it later on. But the maximum number of stereoisomers depends on the number of chiral centers, right? And the maximum number is 2 to the exponent n, where n is the number of chiral centers. So let's say you have a compound that has 2 chiral centers. The maximum number of stereoisomers, 4. Right? Let's take a look at our compound here. So meso compounds, they have more than one chirality center, and that are mirror images, but they are not enantiomers. And some meso compounds are actually the same molecules. Right? So they are mirror images, but they're not enantiomers. Right? You can actually rotate this compound. Where's my mouse? Here it is. This compound to get this compound. Just rotate it this way. Right? So that's a meso compound. Alright, so we've talked about this quite a bit. Now chirality. What is chirality? You're thinking, right? So a chiral molecule is one that cannot be superimposed on its mirror image. Right? And so, classic examples, left hand, right hand, right? And so the spatial connection between 4 substituents of sp3 carbons. So wherever you have an sp3 carbon that has, all 4 of them are different constituents or substituents, then you automatically have a chiral center. Right? And that is a stereocenter. The terms are used interchangeably. Right, so just look for that and you should be able to find it. Right, and here is a nice image. So I personally like this image. It shows you the isomeric relationship between certain compounds. So you know how we talked about diastereomers? So now you can see diastereomers, right? So this and this are diastereomers, this and this are diastereomers. and all the different possibilities. So remember, there are 2 chiral centers. The maximum number of isomers, stereoisomers are 4, 1, 2, 3, 4. Right? There are 2 pairs of enantiomers, and the rest of all relationships are diastereomers. Right? They're non-superimposable, but they're also not mirror images. Right? Like this guy and this guy, they're not mirror images. See, take a look at the bromines. Right? So they're not mirror images, and they're still not superimposable. So that's a diastereomer. Alright, so the next thing here is the Alchemy app. So you guys, I think we're given this guide and stuff online as well. So you're supposed to install it and utilize. This is for Android users. And again, I think you guys were given this on your separately as well, so that's what you can see. So what does the Alchemy app look like? Well, I have a video to show you.
Hi, so here is a quick video on the use of the Alchemy app. For visualizing molecular models. So the first step is you will need an AR target, like the one shown here. This should be available through your instructor, and you can download it and print it, and it will be needed for the proper functioning of the app. So we'll start the app. So here's the main interface. The preferred way to use the app is to select Use Targets, and that will allow it to register onto the target and produce the augmented reality image. Here we are now in the main menu. So now we can look at the various topics that we have available, so everything from atomic orbitals, hybridization, bond formations, as well as various stereochemistry concepts such as Newman projections and chiral centers, which will both be very important in the study of organic chemistry. So let's get started with something simple such as sp3 hybridization. So as you can see, it's already detected my targets, which was placed onto the table earlier. Now I can adjust the size of the image, and I can also play the animation. So there you can see the various orbitals that make up sp3 hybridized bonds, which is a tetrahedral carbon center. The atom itself is not visualized, but the electron cloud are. So you can hit the eye off to the right side in order to get more information. There you go. Alright, so let's go and have a look at a different principle. So now we can go ahead and look at something such as cis-trans isomerism. This is a very important concept when you're discussing double bonds. And here we can see a molecule of 1,2-dichloroethene, and this is currently in the cis conformation. Notice that the chlorine atoms, or the substituents, are both on one of the sides of the double bond. So when we play the animation, notice what happens to the position of the substituents relative to the double bond. So there you go. Now this is the trans isomer, and this is where the substituents are on opposite sides of the double bond. Now we have rotated again, and now we are back to the cis isomer. Once again, let's have a look at the extra information. Alright, now we'll move on to another concept, which is the concept of rotations as a result of single bonds, and these can have impacts when we look at the ways that certain groups are aligned in order to minimize steric repulsion and other properties which can also be useful when monitoring the stability of a certain product or a certain conformation of a molecule. So let's go ahead and have a look at the Newman projections. And this is one of the tools that you would have learned that can be used to visualize the rotations of a single bonded substituents relative to one another. So here we have a molecule where there are two carbons in the middle connected by a single bond. So down here we have an energy level diagram, which is the red line, and that indicates what the current potential energy of the way the molecule is arranged, the atoms, and the repulsions that generates. So we can put our finger along the red line, and as we move it along, you can see how the group on the top is turning relative to the one on the bottom, which is not. So as you can see there in the highest, almost there in the highest energy position, you can move the molecule around, and you'll notice that's when everything is eclipsed. So the right side methyl groups, as well as the hydrogens, are right on top of each other, and that results in what's called steric repulsion. And as we move on, in the staggered conformations, the energy is generally lower, and as you rotate, you have these intermediate eclipsing conformations, but since the methyl groups are not repelling each other, the repulsion is somewhat reduced compared to the peak states. And at the end, that would be where everything is far apart from each other, especially the methyl groups are on completely opposite sides relative to one another, and the hydrogens are not close to each other. So going through the entire app, there's a lot to explore. Various different concepts of organic chemistry are covered in here. So for example, chirality, chair conformations, which are all very important when analyzing reactions. And this is another tool that can help, especially when physical models might be not the easiest to come by. So just as a comparison though, speaking of physical models, we'll have a look at some physical models that I've prepared earlier. So here's the 1,2-dichloroethene molecule that was featured in a demonstration earlier, as well as an sp3 hybridized methyl group, which is this methanol. And here it is, and as you can see, the same visualization is prepared in either case. So that is it for this quick demo of the Alchemy app. Thank you.
Alright, so that was the Alchemy app. Really cool. I think it was developed here at UTSC, so I mean, super cool. And it's a really, really cool app, I think so anyways. And really fun. Alright, breakout group time. Okay, so what we're going to do here is that you guys are going to answer these. I'm going to break you off into breakout groups, and you're going to answer these 3 questions. Please, somebody take a screenshot right here, right now, right, of the questions, and let me know what your answers are. Right. By the way, if you guys are wondering, I think that you might be cut off from that point. Let me see if I can close that. This might be better for you guys. Right, so breakout groups. So the other 3 questions you have to answer. Please email me. Please CC all the other members of your group. Right, I'll give you guys 2 minutes to take I'd recommend really just print screening it, then open up a Word document, save it there. Or take out your phone, take a picture or something. Right? And email me the answers. Please put down B41, practical, people's names, whatever, right? All of it on there. Right, so that I can find it. And that's good. Alright. Breakout groups time. Oh, and after breakout groups, you guys are free to go. As soon as you're done, just email me and you're good to go.
मैं उसकी बेटी की कॉल आई थी, पर नहीं थे कहा बार मैं उसकी बेटी की कॉल आई थी, पर नहीं थे कहा मैं उसकी बेटी की कॉल आई थी पर आई डिडंट पिक अप देखी थी कॉल आई थी but I didn't pick up. I was asleep.
She found it doesn't stay up. She found it stay up Walmart for the big the big
मैं उसकी देखी थी कॉल आई थी but I didn't pick up. I was asleep.